Today we are going to see Davisson and Germer experiment. When the wavelength of the wave associated with the beam of electron shows the same order as that of X-ray, Davisson-Germer thought that if such a beam of electron is reflected from a crystal, the reflected beam will show the same diffraction and interference phenomena as for X-rays of the same wavelength. So, this became the consideration for the basis of Davisson and Germer experiment. Now we'll see the experimental setup. The Davisson and Germer apparatus is shown in the figure, where F is the tungsten filament which emits electron when it is heated by passing a current from a low tension battery with potential V. Let P is a metal plate having a narrow hole S. It is maintained at a positive voltage with respect to the filament F, so that the electrons are accelerated by the potential difference and emerge as a well collimated beam through the hole S. Here we can observe C, which is a nickel crystal with its 1-1-1 phase normal to the beam of electrons. When the electron beam incident on this crystal, electrons are scattered in all the directions by the atoms in the crystal. This D is a chamber in which the electron beam scattered in a given direction from a nickel crystal is received. This chamber can be rotated. About an axis in the face of C, passing through the point of incidence of an electron beam. This front and this back wall of this chamber are insulated from one another, and the whole apparatus is enclosed in an evacuated chamber. This is all about the apparatus and the setup. Now we'll see the method, or we can say how the electrons are scattered. Suppose a known potential V is applied between the filament F and a plate P. The chamber D is set at different angles. and for each setting of the chamber, the current is noted. The current is directly proportional to the number of scattered electrons entering in the chamber in 1 second. Thus, the intensity of the scattered beam is measured as a function of the angle of scattering. The crystal is held in a fixed position throughout the measurements. This crystal is not disturbed at all. The observations are repeated for different known potential difference. Means we are going to change this potential and we are going to take the readings. Different sets of readings for different potential difference. For each potential difference, the intensity is plotted against the angle of scattering. And by doing this, here we can observe such kind of graphs. When the potential is at 54 volt and this is the scattering angle, when the graph is plotted between the kinetic energy and collector current, here is the angle theta which is observed. The peak is observed almost at 50 degree. Here we had the collector current and theta. In between, when a graph is drawn for potential 54 volt, we'll get such kind of curve. This is the intensity curve at constant potential difference of 54 volt. Okay, these are the observations. We got the observation that for theta is equal to 50, we are getting this peak, and for we had kept the potential 54 volt. Now we'll try to calculate by using these values to find out the wavelength. So theoretically, when we put theta is equal to 50 degree and the accelerating potential, or we can potential difference as 54 volt, when we substitute in the equation, that is wavelength is equal to 12.28 upon square root of V, will get wavelength lambda is equal to 1.67 Armstrong. This is nothing but the theoretical calculation. And when we substitute the value of theta by considering a crystal for first order diffraction, the wavelength can be written as lambda is equal to d into sine theta, where d is the crystal spacing and it is 2.15. Theta is the angle at which we got the peak, that's why sine 50 degree, and the wavelength comes out to be 1.65 Armstrong unit. So from this experimental and theoretical value, we conclude that lambda is found to be around 1.65 or 1.67. So from this we can say the experimental value of wavelength is nearly equal to the experimental value is equal to theoretical value. So this is a Davisson Germer experiment, and I stop here. Thank you.